Welcome students, welcome to today's lecture. As you know, vector integration series is going on and today is the lecture 6. Now today we shall discuss about Stoke's theorem. Now before I start anything, you have to know some concepts. Like, see, this is a line. Rather precisely, this is an open line. This is the, say, A is the initial point and B is the final point. You are familiar with this type of integrals. These are called open line integrals. Integration over C f dot dr or integration over A to B f dot dr. Now, these type of integrals are called open line integrals. Why? Because the line is not closed. Now, suppose I close the line and make a circle like this. So this is a closed line. Okay. Now, in case of line integrals, this line integration can be expressed as this closed sign. So this A to B is a open line integral and this f dot dr over this closed contour is a closed line integral. Now, what is the basic difference between a closed line and an open line? In a closed line, the initial and final point are the same. In any point, these points are same. That's why it is a closed contour. But for the open contours, this is the initial point, this is the final point, or vice versa. There is one more difference. Now, when this open line is shown, actually it signifies only an open line. Okay. But when this open line closes, it actually encloses a surface. See, this is a two-dimensional open line AB. It encloses nothing. It's simply a line. But when it closes something, it makes, say, this is a circle, or it may be a square, it may be a rectangle, whatever. But all of the geometric figures or non-geometric figures always encloses a surface. Say, this is the surface. What will be the area of the surface? Pi r square, depending upon the radius. Say radius is r, then the surface area of the enclosed surface by this closed contour is pi r square. In case of square, the area will be a square. A is the length of each line. In case of rectangle, you have the formula, and in case of any geometrical shape, you have the formula. For non-geometrical shape, again, there are some formulas, there are some theorems. So before starting the Stoke's theorem, just know this one thing, that when when a open line closes and encloses some surface, then there is some relation between this closed line integral and, of course, a surface integral. Now, you are familiar with two types of surface integrals. One is closed surface integral and open surface integrals. Now see, this is a open surface integral. Why? Because there is no closed sign. But this is a closed line integral. Now, why this circle is a open surface? Because you can stretch it in any direction. Actually, you are not bound to stretch in any particular direction. Okay, you can stretch it into a bigger circle, you can shrink it into a small circle or any geometrical shape. Now you are free to expand the surface, expand the enclosed surface. Okay, and that's why it is free surface integral or open surface integral. Actually, this surface is not bounded. This surface is not closed. You can easily expand the surface, but depending upon the length of the AB. Say AB length is the 2 pi r, exactly matching length. Suppose I increase the length of this AB and makes a bigger circle greater than this, then that's also an expansion. So this surface, depending upon the length of the line, can be expanded in any direction. Okay, and that's why it's a open surface. At the same time, it actually closes, and that's why it's a closed line. So it is clear that whenever an open line closes, it encloses a surface. So any closed line actually represents an open surface. So what does it mean? It actually means that there is a relation between this closed line and this open surface. And there the Stoke's theorem applies. It says if S be an open, piecewise smooth oriented surface in space bounded by piecewise smooth simple closed curve C, then and F is has continuous derivatives in the domain within that surface S, then we have the relation between the closed line integral and the open line integral as this one. Closed line integral f dot dr equals to open surface integral del cross f dot ds. Now this C is actually traversed in the positive direction. What is the positive direction? The direction is anti-clockwise direction. Okay. Now in the expression there is no n cap, but you can add an n cap here, n cap ds. In your textbooks, often Stoke's theorem is written like closed line integral f dot dr equal to open surface integral del cross f dot n cap ds. So I have included the n cap also. This n cap is actually the unit normal vector along the surface. We all know from the vector concept that a surface is a vector, so it has a direction. That's why n cap is used. But remember one thing, if in your mathematical expression you do not use any n cap, so you need not to explain what is n cap. Okay, actually in most of your textbooks you will see that there is an n cap, but n cap ds or ds vector both are the same. So you are free to use either n cap ds or ds vector. In my upcoming problems, I shall use ds vector. Now in this theorem I have used some technical terms like open, piecewise smooth surface and this piecewise smooth simple closed curve. I have already explained about open surface and closed curve, but what about this smooth and piecewise? Now see, actually a curve C is called smooth curve if it has at each point a unique tangent whose direction varies continuously as we are moving along the curve C. And actually every path of integration of a line integral is assumed to be piecewise smooth. Why piecewise smooth? What does it mean? It means that it consists of finitely many smooth curves. For example, let's take a boundary curve of a square. Now, square has piecewise smooth curves, which consists four smooth curves, four lines that are smooth curves each. So there are four smooth curves which consist the square. That's why square is a piecewise smooth curve. Hope I am able to clear the technical term piecewise and smooth. Now, to be honest, for your graduation level uh, mathematics, if you forgot to write the piecewise smooth technical term, no marks will be deducted. But for the record, it is actually the most precise definition of the Stoke's theorem. Okay. Now, let's move on to our first problem. Use Stoke's theorem to calculate open surface integral del cross f dot ds, where f is given and s is also given. Now see, s oriented outwards. What does that mean? That means the counterclockwise direction, the positive direction, because every surface has two directions. Okay, and this time the outward direction, that is the positive direction, is considered. Now, before I start doing the problems, if you are new to my channel, then please subscribe to my channel, and of course don't forget to hit the notification bell for the future updates. Now, this is the Stoke's theorem. We are free to use any of these, because see, I have written from closed line integral to surface integral, but here I am using surface to closed line integral because I do not prefer to evaluate the surface integrals. Actually, in your exam papers, generally use Stoke's theorem will not be given. This is the first problem, this is the easiest one, that's why I have added the line use Stoke's theorem. You may not get the line use Stoke's theorem. You may get the line evaluate surface integral this, where f is this and this. So in that case, first watch over the format of the surface integral. If it is familiar for you, and if it can be converted into Stoke's theorem by Stoke's theorem to closed line integral, then it's okay. If you cannot convert it, then you may proceed to the normal surface integrals. And if you are new to this video, you can go and check out my previous videos about the surface integrals and about the line integrals also. Things will be clear for you. Okay, let's proceed. This is our surface, elliptical surface, so we can convert it into standard elliptical form, and we need this form for the parametric equation. This is actually x square by a square plus y square by b square equals to 1. So x equal to a cos theta, y equal to b sin theta. So x equal to 1 cos theta and y is equal to 2 square, so 2 sin theta, where theta varies between 0 to 2 pi. Why? Because no octant is given here. Whenever I convert this ellipse, actually it is in xy plane because z equals to 0 is given. Whenever I convert this ellipse into line, it will cover the all 4 octants into D. In 2D actually there is 4 quadrants precisely. In 3D that will be 8 octants. Now since all the axes are involved here, the limit of theta will be 0 to 2 pi. So r can be written as, this r is not the radius, rather the general position vector. So r equal to I cap x, that is cos theta, plus j cap y, that is 2 sin theta. Now we shall use this f dot dr. F is given, so I can convert it into parametric forms, and I know what is r, then I can easily get what is dr, like a simple differentiation. So dr equal to minus I cap sin theta d theta plus j cap 2 cos theta d theta from this, and you can convert the f into parametric forms. Z equals to 0, so there is no k cap, only I cap x square, that is cos square theta, plus j cap 2x, that is 2 cos theta. After the dot product we have this one. Now it can be proceed into general way, but I prefer the more convenient way, the cos square theta sin theta. So sin theta can be written as, this minus can be written as also minus sin theta d theta is actually d of cos theta, and this is the most general, 4 cos square theta, that means 2 into 2 cos square theta, and 2 cos square theta can be converted into 1 plus cos 2 theta. So these are the most easiest forms of integration here. This is cos cube theta by 3, actually the format of integration x square dx, and this is the most simplest form. After doing some necessary calculations, thereby putting the upper and lower limits, we achieve the answer as 4 pi. See, 1, 2, 3, 4, 5. Only 5 lines are required to do this surface integral. If you are not aware about the Stoke's theorem, then you will proceed in general form. See, this is the whole surface form actually, 4x square plus y square. So all the 4 quadrants, or say 4 octants actually, are involved here. So the general procedure of open surface integral will be quite tough for you, because for each quadrant or octant you have to determine the projections, you have to determine separate integrals. So you will have to do 4 integrals. Rather, apply the Stoke's theorem and only 5 steps, and these 5 steps are very easy for you. This is actually the beauty of Stoke's theorem, converting the complex integrals into the simpler integrals. Now let's proceed to our second problem. Same here, del cross f c. This time we have del cross f dot n cap ds. Remember the n cap in Stoke's theorem? That n cap and this n cap is same. F is given in a rather hard format. S is also given, and z greater than 0, oriented outwards, means counterclockwise or positive. Now let's do the first step, and that's the visualization. This is actually a 3-dimensional elliptical shape, because 4x square plus 9y square plus 36z square. Now imagine you are proceeding the integral in general way. So you will cover the 4 octants, 1, 2, 3, 4. 4 integrals, 4 projections, 4 complex mathematics, and then adding the 4 complex mathematics, you will get the answer. But here we shall convert this to a simple closed line integral. And what is the closed line integral actually? Where is the line actually? Contour C. C is this thing. Okay. this elliptical form. To get that, first we put the Stoke's theorem here. Now this is our surface. Since this is the projection along on the xy plane, so what we have z equals to 0, and that's why this is absent here. Only 4x square plus 9y square equals to 36, only for the contour, not for the three-dimensional surface. Remember that. You can also write it down in your examination paper, because that this thing is valid for only the contour C. X square plus 9 means x equal to 3 cos theta, and y square by 4 means y equal to 2 sin theta. These are the parametric form. See, and r can be written as this. So dr will be just a differentiation, minus 3 I cap sin theta d theta. Okay, this is a printing mistake. All the d thetas are missing. Very sorry. I am very sorry. You can add the d theta in your exam book or in your exercise book. Now let's put everything here. Now see, though f is a gigantic thing, k cap is simply excluded here because of the contour. So this is the beauty, converting complex into simple. Now see, after putting the, actually I have done some step jumps here. After the parametric form conversion and the dot product, we have 3x sin theta plus 2y square cos theta theta. Still, I have not used this 0 to 2 pi here because x and y square are still there. Until and unless all the parameters are converted into one to another, you cannot apply the lower and upper limit properly. See, after putting the x equal to 3 cos theta and y equal to 2 sin theta here, we have the third line with the limit integral 0 to 2 pi. Why 0 to 2 pi? See for yourself, all the 4 quadrants are used. Again, this is very convenient integral. Cos theta, actually minus cos theta d theta is d of sin theta, and same applies for here also. These integrals are very much easy for you. I know that you can do it. And see, answer is 0. So what will be the physical significance? Suppose there is one more question, comment on your answer. Then what will be that comment? The comment will be, since closed line integral is 0, first thing, f is a conservative vector. Second thing, f is independent of the path. Third thing, energy will be conserved during the work done f dot dr throughout the closed contour C. So if there is a question, comment on your answer, you have to comment all the 3 important consequences of the result. Often in answer books or in answer scripts, you write casually for the comment like f is a conservative vector only. Then that will not fetch the full number for you. So remember that thing. Let's proceed for the third one. Use Stoke's theorem to calculate the closed line integral. Now this is a quite hectic form because you have to convert this thing into a surface integral, and as you know, generally I don't prefer to evaluate the surface integrals because they are not so complex, not so simple. Now f is given and C is again a little bit complex type of contour. It is actually the intersection between the cylinder and a hemisphere. Now first thing first, if you can, you have to visualize something. What? The intersection. See, what is the C actually is? C actually is this contour. It is the intersection of this hemisphere and the cylinder itself. Clear? But you cannot proceed through the simple line integral. Why? Use Stoke's theorem. So if I use Stoke's theorem, okay, before that we have to clear the intersection plane equation. X square plus y square equals 4, and let's put that 4 in here, and z equals to root over of 12. It is clear for the picture that this plane is not z equals to 0. So z equals to root borrow for the plane. Now the parametric forms. Again, the parametric forms are circular parametric forms. Though in 2D this thing looks like a elliptical path. It is actually a circular path because this is a circular equation and this thing is a hemisphere. So the cutting plane will be a circular in nature. So x equal to r cos phi, y equal to r sin phi, r equals to 0 to 2, and phi equals to 0 to 2 pi. Now you can ask me, why phi? Why not theta? So in regards with the thing that the intersection plane is of first a cylinder with a hemisphere, I have used phi to signify the cylindrical format, but this is actually first a cylindrical, then an hemisphere with this thing. This thing is a circular parametric form. That's why x equal to r cos phi, y equal to r sin phi. But this phi signifies that yes, there is a cylinder in between. Only that. That's why I have used phi. You can use theta for yourself. Let's apply the Stoke's theorem. See, the complex form has been given to you. Now, what is the direction of this ds? See, this is the surface. Okay. Actually, this plane is actually a z equal to constant plane. So, a parallel plane to the xy plane. So, this has only two directions. One, plus k cap or plus z cap direction. Second, negative z cap direction. Okay. Now see, oriented counterclockwise. This means what? You have to depend on the positive direction. So we are taking the positive direction. This is plus z cap. Now, first del cross f. This is a very simple mathematics. You can do that. This gives me minus 3 x square y square k cap. So I have this thing. I have already told you that we are considering the positive side or the positive direction. So ds can be written as n cap ds, and that n cap is actually z cap or plus k cap. Okay, clear? So k cap dot k cap will be cancelled out as 1, dot product is 1, and we are left with this thing. Now, I have already told you that the surface is a intersection between cylinder and hemisphere, and that's why these surface parameters are in cylindrical format, and that's why this ds is actually in cylindrical format, r dr d phi. And after putting the all parameters, we can have this type of integration. Now, what is the benefit of this type of integration? Here, all the integrations are independent to each other. See, there is no r part, See, there is no phi part here. So you can simultaneously solve two integrations at a time. See, this thing gives sine 2 phi, okay, sine square 2 phi, and this thing gives r to the power 6 by 6. So after putting sine square 2 phi as 1 minus cos 4 pi by 2, we have 2 to the power 6 by 6. What is 2 to the power 6? 2 to the power 6 actually 64 by 6. And after that necessary calculation, you have the answer as minus 8 pi. So, though we have used the parametric forms here, this surface integral is quite a hectic for you. What if the question was only calculate the closed line integral? In that case, I suggest you not to go for the Stoke's theorem, rather to stick with the closed line integral theorem. Okay, so let's try the line integral directly. Now this is without using the Stoke's method. For that, we are left with all the previous parameters like z equal to root 2 and x equal to 2 cos phi over 2 sin phi, and all the other things are the same except the theorem. Now here we have our f from the previous one and our dr from this one, and after the dot product we get this thing only. See, this is a way better process than the previous one. Only two lines, but for a surface integral, you know what happens. And these two integrals are very easy to solve. This can be written as 4 cos square theta sin square theta and 2 sin square theta d phi, 2 cos phi d phi. This is very easy. This is actually sin 2 pi square, that is sin square 2 pi, and this can be converted into cos 2 pi like this one. And this is very easy for you. You can do your maths, and the answer will be the same. I have done all the steps properly here, and see for yourself the result minus 8 pi. So I am not wrong, though I know the answer before, but I am not doing any wrong. If in your exam paper the question comes in the format calculate this integral, then do not use Stoke's theorem to convert the simple closed line integral to a surface integral. Rather, use Stoke's theorem wisely to convert the surface integrals into the simple closed line integrals. Number 4, we have our f given. Evaluate this one, where S is the surface of the sphere this above xy plane. Now see, this is the typical question. Nothing has been clearly shown. Use Stoke's theorem or any theorem, or do your mathematics of your own. If you proceed through direct surface integral, then this thing is a three-dimensional above the xy plane. So all the 4 octants 1, 2, 3, 4 is within this surface. So if you do the surface integral, you have to do 4 surface integral and then add them together. Rather, use our Stoke's theorem. This is our sphere. Actually, this is not the sphere, this is the half sphere, hemisphere. Since this is above the xy plane, I have only drawn the above xy plane format. Okay, you can do your drawing as you wish. You can do the dot here, the whole sphere, but irrelevant. Actually, whole visualization thing here is irrelevant. I have drawn only to show you this path. This path is your contour integral path, closed contour path. Let's apply our Stokes theorem first. See the C? C is this path, this closed path. Now, since this closed path is a circular one, so x equal to a cos theta, y equal to a sin theta, where theta ranges between 0 to 2 pi, since all the 4 octants are in consideration. Then we have r as this, and dr is the simple differentiation of r. Okay, there is no spelling mistake here or any typing mistake like the previous one. Now, what is the value of f dot dr? You can do your maths. You can put the values like f is given here, y equal to a sin theta, x equal to a cos theta, putting together here, and after doing the dot product we have a square cos 2 theta d theta. Between the first line and third line I can do the step jumps, you can do the trigonometric formulas. Ultimately we are left with a very simple format. So this is our very simple format and very simple integration, finished in just 3 lines. See how easy is the process and how powerful is Stokes theorem. So always, wherever you can, use the Stokes theorem, but do not use from line to surface. Use surface to line conversion, because that is very easy. In your answer scripts, question will be a part deceiving, because the weightage of this question will be 4. Okay, some students will be confused and do their own maths like direct surface integration. They will get 4. If you apply the Stokes theorem and be the smart work, you get the proper 4. Choice is yours. Now, find the work done by the force in the displacement around the curve of intersection of the parabola this and this. Now, this is a very interesting question, because actually this question is valid in both mechanics part and in mathematical part. See the work done by the force, that means line integral f dot dr. Since it is the intersection of the parabola at this and cylinder this, it is closed, but the main thing is, can you visualize the curve? Because it is the intersection between the paraboloid and the cylinder. To me, it is very tough without any simulation software to visualize the format, visualize the intersection curve. Okay. So, there is one very special thing. Whenever this type of problem is given to you, find the work done this and this, and the curve is a little bit hectic, a little bit complex, always think first that this f may be written as f equal to del phi. Now it is your smart work to evaluate the phi. Here phi is x square y cube sin z. Why? Do I know some magic? Yeah, the f is itself a magic. See for yourself the elaborate process. The del phi equal to, this is the del format in the Cartesian coordinate system. This is phi, and these are the result. This is the result of the 3 different differentiations. Now see the same thing f. Now the process. How will you determine whether f can be determined as f dot grad phi or not? The first indication is the language. Find the work done. See, find the work done by this type of complex f with this type of complex curve with a weightage 3 or 4. Nah, there is something fishy. What is fishy? This f can be converted into some very concise. See, this is the dx I cap, this is the x differentiation. So what is the differentiation of with what gives 2x? X square. This x square gives 2x and y cube sin z constant. Okay. Now the second part, this is y differentiation part. Which one gives 3y square, y cube, x square sin z constant. See, x square y cube sin z. Already you know that. Already you have the conclusion that phi is x square y cube sin z. What is the conforming part? See, x square y cube conform. This is the z differentiation format cos z. What is the differentiation of sin z? Cos z. So the format though looks a little bit lengthy, little bit complex, it is very simple indeed. This f gives you the hint that okay, the mathematics is very simple, there is some trick. Here is the trick. I am the phi equal to x square y cube sin z. So it is your concept which will bring you the f equal to grad phi format. Remember one thing, I am giving you the guidance only. In your exam or in the practical scenario, you will have to evaluate all the problems by yourself. I am here only to guide you through some different problems only. I cannot do the problems for you. It is you who have to determine the type of the problem, the path of the problem and the way of the problem. Whether it will be a complex one or you have the ability to see the tricks and convert it to in simple form. It is you, but with my guidance. I can guide you through some different problems. Okay. To achieve the expertise, you have to do some rigorous problems. In this short video, though this is not a short video, it may be a 40 or 50-minute video, quite long for a YouTube lecture, but it's short video for me. In here in this short videos, I can only guide you through some different type of problems. Okay, rest is up to you. You have to practice some different problems. Okay, now back to the problem. So the work done, f dot dr. Now since this closed line integral c is a little bit complex for you, you can convert into the surface integral. Now this contradicts me because I always prefer the simple line integrals, but here is the trick, because see for yourself, you have f equal to grad phi and you know del cross del phi equals to 0, del cross del, that gives us 0. This is the standard format of vector differentiation. That's it, finish. So 1, 2 and 3 lines. Okay, 1, 2, 3, 4. 4 lines, 4 or 5 lines. And this complex maths is completely finished into 0. So this is one of the trickiest question. Okay. In the cases where f can be written in form of del phi, you know that apply the Stoke's theorem, convert the line to a surface, then del cross del phi will be a 0. Why? Because when f can be written as grad phi, only and only f is a conservative vector. You already know that f is a conservative vector. So the integration will be a 0, but you have to do the maths also and in the proper way. So this is the proper way. Now we are confirming our answer, thereby doing the hard way, del cross a. See, I cap this one minus j cap this one plus k cap this one, and each time both the terms will be cancelled out. Both the terms will be cancelled out, and this is 0. Now, why I have done this del cross f equals to 0? Because in some cases you may face the question, support your answer. For that part, you will have to do the maths like this one to support that f is a conservative one, or rather you have the answer like this. Find this work done along this path, comment and support your answer. That's also a tricky part. 3 plus 2 weightage, you get the 3 for this thing and you get the 2 for confirming this thing. Okay, now use Stoke's theorem to calculate f dot dr where C is the circle given cut off by the plane z equals to -3 oriented counterclockwise, so positive direction, as seen by a person standing. Okay, that's also general format. F is given. Now this thing is a little bit interesting form because C is the circle at z equal to -3. Okay, let's visualize the problem like this. See, this is quite a unique problem. Why? Z equals to -3 case. So this is the first octant z equals to -3. Now z equal to -3 will have two directions, generally two, plus z and minus z. Since this is the counterclockwise direction, so this circle, this line is counterclockwise, so the direction will be in the outer part, in the positive part. Now on the plane z equals to -3, what we have, f equal to, put z equals to -3 in each part. So we have a clean and clear f containing only x and y. So the math becomes easy because this is the contour in the xy plane, and as I have told you, we will adopt the positive direction, positive z axis, and that's why ds equals to k cap ds. Clear? Okay, now let's put the del cross f. Why del cross f? Now we are going to convert the closed line integral into a surface integral. Before that, we know that del cross f dot ds. So ds is given and del cross f is given. Now again you will question me, why are you doing this? Why are you doing the hard way? Believe me, first go through the total process and you will notice that this is not the hard way. Now why I have used this format fx, fy, fz? Because I am not going to expand this del cross f. Why? Because in Stoke's theorem, del cross f dot ds, this is along z direction, so we need only the z direction, k cap direction, and that's why I am not gonna expand this into the whole xyz directions. We have del cross f dot ds, like this is along k cap, so we need the k cap direction, like k cap del x of fy minus del y of fx. Okay, this is our fx, this is our fy, simple minus 28 ds. Clear that? Okay, now let's apply the theorem. We have minus 28 surface open surface integral ds. Now what is the surface integration? It is actually a circle of radius 2. So what is the formula of a area of the circle of radius 2? Pi r square, where r equal to 2, pi into 2 square, 4 pi. That's it. Minus 28 into area of the circle of radius 2. Minus 28 into 4 pi. So minus 112 pi. Very easy. Very easy. See, whenever this type of problem comes, when you are very confused about the C or the contour, you can use the surface integral depending upon the problem, which gives me the judgment that I have to use the surface integral here. See, first of all, z cut off by the z equals to minus 3. Z equals to minus 3 planes or z equal to constant plane means xy plane. Okay, now xy plane gives two directions, plus z and minus z. Since this is counterclockwise, plus z is fixed, so it is better used surface integral because only one component, k cap ds. Again, what is this ds? ds is a simple geometrical form, simple circle. See, if you cannot draw the problem, you can have, what is C? What is the S actually? S is actually a circle of radius 2. So integration ds, what does it mean? Pi into 2 square. Simple integration. So actually, while doing the surface integration or the Stokes theorem integration, you will have to identify the small informations behind the question. The small informations are the powerful tool. They are the tricks for the smart work. See, this is actually the smart work. Otherwise, you are free to do the normal closed line integral, and that will be at least 12 to 15 steps of mathematics. Now see for yourself, hardly a 5 to 6 steps here. So again, I am telling you, I am giving you the examples of different problems. I am giving you the advice. Now how to use that advice, it solely depends upon you. I have already shown you some simple problem, tricky problem, and the most trickiest problems also. Now you have to do rigorous practice, because practice makes you perfect. Actually, if in your answer script the weightage is 4, then I prefer not to use this area of the circle of radius 2 term. Rather use the polar format. If you use area of the circle of radius 2 pi r square, that is not wrong, that is perfectly or technically perfectly right, but it depends upon the weightage. Suppose the weightage of this problem is 3 or 2, then you can use the pi into 2 square. But if the weightage is 4, then there is some questions arising whether to use it or not. It's my personal view not to use for weightage greater than 3. Okay, weightage equal to 3 or less than 3, use this simple format. But weightage greater than 3, please use the conventional surface integral, that is the polar format. Okay, this is the simple polar format r dr d theta, and limits are given. Answer is same. Only this is conventional method and this is simple trick. But if this question comes at any MCQ type competitive exam, then you are free to use this thing. Then I strongly recommend use this thing, because in that competitive exam time matters. Okay, so that's it for today. Hope you have enjoyed well. Thanks for watching, guys. See you soon.